All right. So here's what we were doing last time. I just kind of copied what we already written. And so this is an example to show how banded matrices come about in a very natural way. So we're looking at an ODE, second order ODE, y double prime minus py prime minus qy equal r on an interval from a to b. And we want to discretize this to kind of numerically compute a solution. So we put, endpoints in between A and B. These are the points x1 through xn. The step here has a given formula in terms of n. And the idea is that we're going to approximate the solution at those points xi by a value yi. Y0 and yn plus 1 are fixed. The derivatives are going to be approximated using difference quotients. And then we did the first and we did the second derivative. And we put it all together. Pi, Ri, and Qi are given by the problem. And we put everything together. We multiplied by h squared to get rid of a small denominator. So I multiply by h squared. I also then kind of move things around so that I can write it as a tridiagonal system of equations. Here, yi minus 1, yi, and yi plus 1, those are the unknowns. Everything else is given to me by the problem and my choice. H is given by n. So h is really small. And we call bi these coefficients, ai these coefficients, and ci those coefficients. And now we're going to write it in matrix notation. And notice that, so these equations hold for I going from 1 to n. But equation 1 and equation n are kind of special, right? For instance, in equation 1, when I is 1, then I minus 1 is y0, which is equal to alpha, right? So that's already part of the problem. So, and also when I is n, then I plus 1 is going to be equal to beta. Right? So in that case, these become kind of constant coefficients that go to the other side. So the ax, sorry, we want to write ay equal b, right? We want to write a system like that. So the vector b, not to confuse with this bi, this is the vector b, is going to have this number minus a half h squared ri. But then for I equal 1 and I equal n, it will have an extra term coming from, the alpha or the beta. And then the coefficients are going to be tridiagonal like this. So most of the time, you have 3 coefficients, the rest are 0. And then for the first row and the last row, you only have 2 coefficients. That makes sense?
Yeah, thank you. I was looking at this before class because I got lost in the transcription from the equation to the vector b. I'm with you now.
All right. Okay, so we want to solve this tridiagonal system, but we're going to do something clever before solving that. See, notice that this is not a symmetric matrix. It's not. All right. So why don't we try to make it symmetric? All right, so how would we go about doing that? Let me just show you kind of the trick. The trick is to take D to be a diagonal matrix with the following entry. 1 square root of C1 over B2, square root of C1, C2 over B2, B3, etc. And then we do the following. Instead of AY equal B, we multiply by D, and then we do a change of variable. So we'll add X. So basically I'm going to write this as dA d inverse dy. So X is going to be dy. Either X or maybe let's call it, to be consistent with my notations, I'm going to call it tilde. And then A tilde is dA d inverse. And so then I'm getting A tilde Y tilde. All right, so I'm going to do that. And let's see what, so when you multiply from the left by a diagonal matrix, what happens? Do you remember? All right, so
let's multiply, we permutate the rows, right?
you multiply the rows, exactly. So if you have your rows, A, rows of A where A1 minus C1 minus B2, A2 minus C2. etc. Right, so when you multiply from the left by D, every row is multiplied by the corresponding. So A1, C1 stays like that. And then here, I'm going to get minus root C1 B2. Right, because the root B2 in the denominator will cancel with the B2 there. Like that. And then when you multiply by the inverse of a diagonal, you just take the reciprocals, right, of these things. But now these reciprocal are going to multiply the columns. Right? So the first column is untouched. Right? Because it's multiplied by 1. The second column gets multiplied by the reciprocal, B2 over C1. So that, so B2 over C1, so that gives me this. Then it canceled there, so I'm left with A2. There, right? So you see how it becomes symmetric? It's kind of clever the way it's set up. All right, so this now, A tilde is symmetric. Of course, that's not a proof, but you can prove it. All right, and the other thing is that we didn't do anything super dramatic here, because when you multiply a matrix from the left and the right like this by a non-singular matrix, this operation is called a similarity. So A and A tilde are similar matrices. In particular, so this is the formal definition of similar matrices, right? So they're conjugate. Another, in algebra, this is called a conjugation. They're conjugate with a non-singular matrix S. But so they're similar. So in particular, they are going to share the same eigenvalues. They have the same spectrum. So in particular, they have the same. Right? Let's verify that. So suppose that AU is lambda U, right? Then A tilde Well, A tilde is SA, let's use S here, or we can use D, it doesn't matter. Let's use D. So then it's dA, D inverse. So I'm going to apply that to du. Right? They have the same eigenvalue, but not the same eigenvectors. Yeah, the eigenvectors are shifted by D. And so then this is going to be dA, D inverse du is going to be dAu, which is lambda u. Then the lambda comes out, lambda du. All right, so different eigenvector, but same eigenvalue. And, and you can go backward by the same exact argument. And now the claim is that A tilde is SPD, symmetric positive definite. And with that, then we can use the Koleski algorithm, which is faster. All right, so how do we prove? Is everything clear so far?
Yeah.
So I need to ask you, how is your, are you okay with complex numbers? I promise we were doing everything with real numbers, but then this, I guess, could be used.
Yeah,
in
should be
You
good
can-
to go. Tend to
I'm
forget
comfortable with
half
them.
the identity.
All right. So the claim that that this is a positive definite will follow from a very important theorem with a kind of hard name to pronounce here, Gersh-Gorin. Have you ever seen this theorem before?
Just
I
this
have
morning
not.
when I was looking at bounding.
Right. So
Matrix.
Gersh-Gorin says, and I'm going to do it in the generality of, complex n by n matrices, but it doesn't matter. You can apply it just as well to real. You look at the elements on the diagonal, and so BKK, these are complex numbers. And so you can think of them as points in the plane. Complex plane. And then for k equal 1 to n, you set Rk, a radius, equal to the sum of the entries in the row k. Of the matrix. So the off-diagonal terms in the row. So these are the of diagonal terms in row. All right, so now you have this zk and you have this radii rk, and you can put some disks around each point. And you're going to let S be the union, it goes from 1 to n, of these disks. So I don't know how to, I don't want to use the letter B because B is already used. I'm going to use the letter D. A disk centered at zk of radius rk. And so dzr is the set of complex numbers w whose distance from z is less than right? And I guess they are open disks. And the claim then of Gershgorin theorem is that if lambda is an eigenvalue of the matrix B, then this eigenvalue needs to be in the union of these disks. In other words, these disks are going to cover the spectrum of is the statement clear?
Yeah.
So let's prove Gershgorin theorem first and then see how we can apply that to prove that A tilde is SPD. All right, so if lambda is an eigenvalue for B, that means that there is a vector x, non-zero, such that B of x is lambda of x, right? And in fact, any multiple of x will do the job, right? So actually, we can take anything in here. So we can always scale x so that, let's say, the infinity norm is 1. Right, that you can always do that. And then we can find the entry k such that x of k is equal to this maximum, right? This is the maximum of the, j 1 to n of xj. Now, it could be that the maximum is attained at an entry that's negative, right? Because we have the absolute values here. But if that's the case, then just multiply by -1. So both of these things are a consequence of the fact that any multiple of x satisfies this. All right, so this is just the setup. Now let's go and look at what this actually means. All right, so on the left, we have lambda xk, but xk is 1. So we have lambda equals lambda xk, right? So this is 1. And then this is the same as bx. So we can use the matrix notation, run a counter from 1 to n, bkj. That makes sense?
Yep.
All right. Now, let me split this up into the k term and the rest of the terms. Now, this is 1 here. And bkk, I can move to the other side. Right, so I get that lambda minus bkk is equal to the sum of bkj. All right. So, and remember, by our notations, bkk is a complex number. It's actually zk. So that means that lambda minus zk, if I take the absolute value and I use the triangle inequality, is less than if I put the absolute values inside. But these guys here, they're all less than 1 because the infinity norm was 1. Right, so this is going to be less than RK. All right, so that's the proof of your scoring. If you have an eigenvalue, it's going to be covered by one of these balls or disks, within one of these disks. Okay. It's a very useful thing, especially when your matrix is diagonally dominant, meaning that the diagonal terms dominate are bigger than these sums of off diagonal terms. So all right, so now let's prove the claim. So the claim is that A tilde is positive definite. But remember, A tilde and A have the same eigenvalues. So it's enough to show that that the eigenvalues of A are positive. Right? A is not symmetric, unfortunately. A tilde is symmetric. They share the same eigenvalue. If I can show that the eigenvalues of A are positive, then A tilde will be positive, definite, and symmetric. We need the two things. Right? So, all right. So, what is A looking? What are the rows of A? The rows of A, if you remember, they look. There's a minus BI, there's an AI, and there's a minus CI. So the rows of A look like that. So that means that Zi is AI, and Ri, I'm just translating it in the Gershgorin theorem, and Ri is just the sum, of minus Bi and so you get rid of the signs. And Bi and Ci, they had formulas. They were 1/2 1 plus h over 2 Pi plus 1/2 1 minus h over 2 Pi. It actually very nicely cancel out, and you get 1. And so now what do we need to check? Well, it'd be nice if this was diagonally dominant. So it'd be nice if this was less than the size of Zi. So the question mark is this, well, strictly less than AI. Why would that be nice? Well, because if we have the AIs and they are bigger than 1, then if we can show this, that AI are bigger than 1, then when we take the disk of radius 1, we will find that the eigenvalues stay away from 0. So they're going to be positive. That makes sense?
Yep.
All right, so the question is 1 less than AI? But remember, we had a formula for AI as well. I'll go back up here. Yeah, so this was the BI was here, CI was there. AI is 1 plus 1/2 QIH squared. And so, and in fact, part of the hypothesis was that QI was always greater than some Q positive, right? For every I. This was sort of in the hypothesis. At the very beginning, we had that. So not only the AI, I mean, they are going to be kind of uniformly away from 1. Because h squared is positive, 1/2 is positive, QI is positive. It works out really well. So we get that the spectrum, so by Gershgorin implies that the spectrum is the union of the disk centered at AI minus 1. And this is a subset of, well, when you intersect with the real line. All right. Questions? So this kind of ends the example, and kind of shows how in practice you can actually use faster algorithms if you are, if you are careful in how you set it up. Any questions? All right, and so since we're doing these kind of examples, let me do one more example that's a higher dimensional one. I'm only going to go up one dimension. You can go up many dimensions if you want, but so the next example will be some domain in R2. And so something like this, omega, or maybe, something more rectangular. You can, you can have whatever you want. And let's think about a PDE here now instead of an ODE. Now, the most important PDE, I mean, period, the most important period PDE PDE stands for partial differential equation, is the so-called Laplacian. Right, so the Laplacian, delta U, is two derivatives in X plus two derivatives in Y. Okay, so that's the formula. Two partial derivatives in X, two partial derivatives in Y. And the most sort of general problem you can try to solve is to try to find U that has a given Laplacian if you have a point here, xy, you wanna find a function U with that Laplacian, and also you wanna impose that U restricted to the boundary be equal to some function G. So out here, then U needs to have some boundary values. Okay, this is called the Poisson problem. But very often, before you go and solve this problem, which is a bit harder, you can just do the Dirichlet problem. So, which is the same thing, but now you ask for the Laplacian to be 0. So here is all for you. All right, so that's the Dirichlet problem and the Poisson problem. All right, so let's try to set up this problem in a simpler domain, namely in a square. I'm going to take so this is 0, 0, 1, 0, 1, 1. That's my omega. And so I need to have some boundary data. And so these are going to be functions, G1, G2. The functions G1 to G4 are given. That's what data means in Latin, right? They're given. All right, so how would we go about discretizing this problem, right? We're gonna do kind of similar, there are many ways, but I'll show you one way. Well, you're gonna have some step sizes in both directions. So for instance, ux, in the horizontal direction, you have some nodes, say nx plus 1, and in the vertical direction, some mesh nodes ny plus 1. So I'm allowing for maybe having different subdivisions here, although I don't see why you would do that if you have a square. But it kind of, you know, trying to imitate what we did in the previous example, where now the interior points are the points where xi, yj, where I is between, say, 1 and x, j between 1 and y, and then the other ones are going to be boundaries. So these are the interior. And if you think about it, by the way this is set up, this point here is going to be I times the step in x and j times the step in y. Because that's how we've set it up. All right. So is that clear so far?
Clear enough, I think.
All right, so now we're going to do the same thing as before. We want to kind of approximate the partial derivative. So for instance, two derivatives in x, right? At a point xi, yj. How would you approximate this? There are many ways to do it, but let's do it this way. So here, this is xi, yj. It's going to have 4 neighbors. right? And this is going to be xi plus 1 yj, xi minus 1 yj, xi yj plus 1, and xi yj minus 1. And we have these 4 points. And the two partial derivatives in x, we can think of the second derivative in the x variable, right? So it's going to be xi plus 1 yj minus 2 xi yj plus xi minus 1 yj over over, what was it again? This is actually exactly the same formula as before, over hx squared. Right, so I'm claiming that the two derivatives in x, you fix the variable y, and then you just take a second derivative. So it's exactly the same formula as we had here, this one. Right, same formula as before. But then we're going to have to add the two derivatives in y, which is going to be the same formula, but in this direction. Anyway, let me finish this calculation next time since I ran out of time. Let me know if I have to. I'll try to catch you up again.
Okay. Cool. Thank you, sir.
Let me know if you have any other questions.